about function composition. So on this next page, there are going to be a whole lot of words, okay? You do not need to write down everything that is on this page. You just need to kind of listen to my explanation, okay? So the reason why we talk about composition of functions is because a lot of times in the real world, it's not just one single function, but a combination of functions. So we've dealt with combining functions before. We've added, subtracted, multiplied, divide, all that stuff. But, for example, sine of x squared actually comes from two functions. When you think about plugging in a value there, you would plug in the x value. You would square it first, then you would plug that value into your sine function, okay? So that is actually a composition of functions because you do something before you do another operation on it, okay? So here is the technical definition of the composition of functions. If we have two functions, f and g, here's our composition notation. Sometimes we use this little circle. FOG looks like fog. Okay. I prefer the parentheses kind of notation here. You read that f of g of x. Okay. F of g of x. And so when we're trying to analyze that, we start by plugging our x value into g. We get that answer, and then we plug that answer into f. So that's the notation. Let's actually look at composing some functions here. We're going to find f of g of negative 1 and g of f of negative 1 and g of f of 4 if these are our f and g functions. Now, if you remember much about composition of functions from Math 3, you'll know that we can algebraically plug the g of x function into the f of x function, simplify, and then plug in the answer. But if you're just evaluating, in my opinion, it's easier to just plug in the number. Like I said, you start kind of on the inside of this function. So if we're trying to find f of g of negative 1, I start by plugging negative 1 into my g of x function. So g of negative 1 is equal to, and I'm going to do this without a calculator because I'm trying to get y'all to practice more without a calculator. Negative 1 squared is positive 1. So that's 2 plus 7 plus 4, so that's equal to 13. So then we do f of 13. G of negative 1 is equal to 13, so we replace g of negative 1 with 13, and then we plug 13 into our f of x function. 13 minus 5 is 8. So that is the answer for f of g of negative 1. Now, let's find g of f of negative 1. It looks like it's the same thing, doesn't it? Or it should be. Because we're evaluating it at negative 1. Why would it be any different? Can anybody tell me why it would be any different? The order matters, right? Because in this one, we're going to plug negative 1 into f first, which gives us negative 6. And then we're plugging negative 6 into our g of x function. So very different than what we did before. So that's 2 times 36 plus 42 plus 4. So that's 72 plus 42, which is 114, plus 4 is 118. So two very, very different answers for notation that initially looks very similar. F of g of negative 1 and g of f of negative 1. The order does matter. The order matters big time. And just for practice, let's do another one. G of f of 4. Now, I throw this notation in there. It is not as widely used. It's not. Most of the time, you're going to see it using the parentheses, but a lot of times when this notation pops up, it throws people off and they think that they're supposed to multiply by 4 or something like that. So anytime I see that notation, I automatically just go ahead and write it using the parentheses so that I'm not messed up and thinking that I need to multiply by 4 or something like that. Okay, plugging 4 into f is very simple. 4 minus 5 is -1. Have we already found g of -1? Yeah, we did that a second ago. It's right up here. G of -1 ended up equaling 13. So why do the work again? Just use what you did before. Okay, so g of f of 4 is equal to 13. Pretty straightforward. Okay, now let's look. What if they don't give us the entire function? Okay, what if they don't tell us that f of x is equal to x minus 5 and g of x is some quadratic? What if they just give us a table of selected values? We can still do this, okay? And it's actually less work on our part if they just give us a table of values, because all we have to do is pick it out of the table. We just got to remember to keep our order straight. Okay, so if we're finding f of g of -3, all we're going to do is go to the table. We've got g of x. We find when x is -3, the y value is 4. So g of -3 is equal to 4. It's in the table. Instead of us having to plug it into a function, what happened was when we plugged -3 into the g function, the answer was 4. And then f of 4, we go to the table. F of x is the second column. 4 is right there. So its value is -9. That is your answer for f of g of -3. Okay, g of f of 2. Okay, f of 2 from the table is 0. G of 0 from the table is 5. How about, we know the order matters, so how about f of g of 2? Well, g of 2 is -1. And f of -1, we got a problem. -1 is not one of the x values on our table. So don't say that it's undefined, because it probably is defined. It just cannot be determined because they didn't give us enough information. Okay, cannot be determined, not enough information, something of that sort. It probably does exist. They just didn't give us enough information in the table. Okay. Now, I don't have an example like this in the notes, but since we're looking at this table right here, let me point out something really quickly. I could do the exact same thing with this if I was given a graph of the two functions. Okay, if I had a graph of f of x and I had a graph of g of x, I could answer questions like this, because what does a graph tell us? When x is this on the graph, it tells me the y value at that x value. Okay, so you should be able to extend this concept to a graph as well. All right, let's look at just evaluating it algebraically. Okay, we're not plugging in a specific number. We're not evaluating it at a value. We are just trying to compose these two functions. Okay, we've got f of x is the function x squared, g of x is the function the square root of x plus 1. We want to find f of g of x and g of f of x, and we already know that the order matters, but these functions are probably not going to equal the same thing when we compose them. Okay, so let's do f of g of x first. Now, this is the way that I like to do it personally. It helps me visualize. What I do is I replace g of x right there with its function, the square root of x plus 1. So then I know that I am taking that just like I would take a number and plug it in everywhere I see x in my f function, I'm just going to plug in that expression. So I replace that x right there with this expression, just like I would replace it with a number, and it's squared. And when you square a square root, those cancel. So this composition ends up giving me the linear function x plus 1. Okay, let's do g of f of x, and then we'll look at the graphs. All right, so we're going the other way. I'm going to replace f of x with its function, x squared. And then that means everywhere I see x in my g of x function, I'm replacing it with x squared. Now, I can't simplify anything with this one because I can't take the square root of x squared and the square root of 1 because they're separated by a plus. Okay, if that was just multiplication, sure, but I can't do it because of that plus sign. So that's as simple as that'll go. So obviously two very different functions here. Now, we know obviously what x plus 1 looks like. It's a line. But let me show you that this is actually supposed to have a restricted domain, and we'll talk about why in a second. Here's what I'm going to do. I'm going to show you how you can kind of check this in your calculator. I'm going to plug f of x into my y1. I'm going to plug g of x into my y2. Okay. And in y3, what I'm going to do is I'm going to make the calculator do the composition. And the way that I'm going to do that is I go to vars, which is right beside your clear button. And I go over to yvars and press enter and press enter. So I'm doing f of g of x. So f was in y1. So y1 of vars, yvars, enter y2 of x. Okay, so what I did, I'm just putting the composition notation, but instead of using f and g, f's in y1, g's in y2. So that's the composition f of g of x. And I'm going to, I don't know if y'all know that you can do this, but you can move your cursor over to the equal sign, and you can press enter. And so it has that stored in there, but if the equal sign is not highlighted, it's not going to graph it. So when I press graph, the only thing that's graphing here is my composition. Okay? So it looks like a line, but notice it doesn't stretch across my entire screen. Here is why. Because when I compose this, the first function that I have right here has a restricted domain. Remember doing square root functions? We have restricted domains because we can't take the square root of a negative number. Okay, so as long as our x's are -1 or bigger, we're good. Okay, as long as our x values are -1 or bigger, we're fine. So that restricted our domain. When we square it, that's no big deal. We can square any number that we want to, but we can't take the square root of any number we want to. So that's why when you graph this, it looks like the line x plus 1, but it's not the entire line x plus 1. It starts right here at -1. Okay. Now, do we have a similar issue? Yes. Okay. So to just graph the composition, you go over to your equal sign and you press enter. If it's black, it's going to graph it. If it's not, then it won't graph those. Okay? So, tell me this, before I do it in the calculator, am I going to have a restricted domain for this function right here, for g of f of x? Are there any restrictions on x squared? No, no restrictions there. How about with this? You can't take the square root of a negative number. Is x squared plus 1 ever going to be negative? X squared plus 1 is always positive. So I don't believe that there's a restricted domain. Let's check it. I need to change the order here of y1 and y2. So y2 of y1, g of f, Okay, we'll graph this one. All right, so it kind of sort of looks like a parabola a little bit, but it's just really stretched out and wider. Well, it's probably more similar to an absolute value, wouldn't you say? But anyways, my point is, we don't have any missing x values. It doesn't just appear out of nowhere. There are no restrictions on the domain there. Okay? So, let's practice